This is section 4 of part 2 of section 4, of unit 10. We are going to talk about inscribed polygons today. Now I went ahead and left some information on my screen to make it easier as you guys are listening to write this stuff down. The first thing I want to say is a polygon is an inscribed polygon when all its vertices lie on a circle. Notice it has to lie on the circle. The circle that contains the vertices is a circumscribed circle. Excuse me. In my first theorem, we're going to talk about right triangles, or inscribed right triangles, I should say. And this one is if a right triangle is inscribed in a circle, then its hypotenuse is a diameter of the circle. Conversely, if one side of the circle is an inscribed triangle, or one side of an inscribed triangle is a diameter, then the triangle is a right triangle, and the angle opposite of that diameter is the right angle. That's a lot of words, so I'm going to break it down for you. What I am saying here is that because I have a diameter and a triangle created with that, I officially have a right triangle. So that angle opposite the diameter will be my right angle, and my diameter is going to equal, or my diameter is, the hypotenuse. So this is just a nice little reminder. The diameter is always going to be the hypotenuse if I have a triangle inscribed into my circle. And then, like I said before, this lovely angle that is opposite, and I went ahead and drew the arrow right here, the lovely angle that is opposite that diameter is going to be the right angle, making these my legs. Excuse me. So let's go ahead and solve an example here. So I'm given a triangle inscribed into the circle. I know it is because all three of my vertices touch the outside of the circle. So that means this here is my diameter, making this my right angle. So I'm going to have 2x is going to equal 90, which means x is going to be 45. Pretty easy. Utilize this information to solve for any of the missing sides if you're given the diameter and it says find the other sides, or any of my other angles as well. So coming down here, I have one last part to this, and this is actually the inscribed quadrilaterals. And I'm going to zoom in on this part here. So I'm saying that a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So back in chapter 7, we talked about how the same side is going to be supplementary and opposite are going to be congruent in a parallelogram. However, I'm talking about general quadrilaterals that are inscribed in a circle. And this just means that instead of going next to each other, I'm going across. So D and F, angles D and F are going to be supplementary. Angles E and G are going to be supplementary. So if I'm trying to solve, I'm going to say that the measure of angle D plus the measure of angle F is going to equal 180 degrees. Likewise, I can say that the measure of angle E plus the measure of angle G is going to also equal 180 degrees. So coming over here to my example, once again, I need to make sure I go across. Ooh, that was funky. That's not much better. There we go. So I'm saying that the measure of angle E plus the measure of angle G is going to equal 180 degrees. So I have 120 degrees plus the measure of angle G, which we actually have marked as Y, is going to be equal to 180. When I subtract 120 on both sides, I have Y to equal 60, so I'm going to go ahead and state that the measure of angle G is going to be 60 degrees. Now coming over here, I'm going to go ahead and do the other pair. So right there, D and F. So I'm saying that the measure of angle D plus the measure of angle F is going to equal 180 degrees. We say that the measure of angle D we have marked as Z. That's going to be the measure, or added to the measure of angle F, which is 80, and that'll equal 180. When I subtract 80 from both sides, I get z to equal 100, which makes the measure of angle D 100 degrees. Excuse me. So those are going to be my two answers for this example here. And that is inscribed angles and polygons.